Music. What's it all about? In this video, we're going to consider just that question. So I'm playing one of my favorite musicians at the moment, and she's called Gabriela Quevedo. She plays a fingerstyle guitar technique, and she does a really great job at doing covers. Okay, so I recommend that. Now let's get on to what we're doing today. So I'm looking at this booklet that I made, a YouTube course in Mathematica, and today we're going to do audio exercises in Mathematica. So let's move to page 112, where we find the audio exercises. Now, first of all, I'll point out my disclaimer. Be careful when you're doing this, because if you're multiplying sound by a number, what that does is it increases the volume. So if you're not careful, you can get a very loud volume, and that can be very dangerous for your ears. So before you try this, I suggest don't do it with headphones, do it with the speaker and turn the volume to a low enough level. Okay, having said that, let's get on to the exercise. Okay, so the first one says try out the following, modify it, compose your own song, export it as an MP3. Okay, so that's a basic exercise to get started with. So I've already got this typed out. Okay, it is right here. Song equals, now it's play, and then you put in the function of t, and then the range for how many seconds you want to play for. Okay, so shift enter. There it is. When we press play, now hopefully it's loud enough for you to hear through my bad speakers. Okay, so I'll play it. Beautiful. Did you like that? Okay, so then if we are to follow through with the instructions, modify it to compose your own song. Okay, well, what do you want to do to it? So let's change the frequency of the cause function. What if we just how about we just square this t? That'll change it. Okay, and let's multiply this by 30 instead of 20. Okay, shift enter. All right, we have something else. Let's play it. That was interesting. All right, great. So if we're happy with that, now let's export. So right, export. And then we need to call it something. So let's call it our song.mp3. And then I'll have to put a comma and say what I want to export. So if we go up here, it'll be song, because that's what we've called it. Okay, so I'll put that song and shift enter. All right, and down below it says our song.mp3. Now I've got to go into the documents folder, which is the default folder for where Mathematica puts things that I import and export. All right, so let me open that. All right, now I'm looking through my documents folder on my computer, and I found something. I'll put it on the desktop here, or I'll just open it up. Okay, did you hear that? So I'm using VLC Media Player. I'll play this. I'll turn up the volume a bit. Play this. Okay, there it is, and that is an MP3 file that I've got produced by Mathematica and put in the documents folder. So that works just fine. Now I should say that if you're using Mathematica 10, which comes for free on the Raspberry Pi, then the code in this exercise will be slightly different. All right, so just know that. I'm using Mathematica 11, and we're soon up to Mathematica 12. Okay, so let's do the next exercise. Try out the following and explain what the functions do. Okay, well, I'll give this a go. let's have a look. So first of all, we want to put in s equals table, and then I'll tabulate. T goes from 0 to 1, and then we've got 1 dot over 2000. Okay, so we're saying that this is in small increments, I think. Right, anyway, so let's just put in sine 2 times pi, so this is 3.14, etc., times 500 times t, and then add, I'll keep the brackets, 2 plus cosine of 20 t. All right, shift enter. What do we have? We have a list now, right? That's not surprising. So this is a list of data. Okay, so this suggests that from data we may be able to produce some sound, right? So let's have a look at the rest of this, and then it says sampled sound list. Okay, this is a built-in function that probably is going to give us some sound from that data. So let's try this. I'll put a semicolon here, and then we have some space to write this. T equals, and it seems as though I should shift this to the left so my head's not in the way. T equals sampled sound list. S. So S is that array that we built above. S, and I think this must say 2000 elements of that list. Okay, so we're setting this into memory. Okay, so then the next command says sound t. Okay, so let's actually have a look and see what that looks like. All right, it just puts this command around it. All right, so you don't get anything out of it really until you say sound t. In other words, to interpret this as sound. Okay, and now if we look at it, we see what looks to be something we can play. So let's press play. Okay, so there's some sound. Okay, so yeah, so basically what you should get from that is from data you can generate sound. All right, let's have a look at the next exercise. Which says download and copy the files entitled It's Your Birthday by Monk Turner and Happy Birthday to You by Soren Urzika, and place these into the document folder or another two MP3 files that you might have ownership of. Okay, so I think I've got one of these, which is the first one by Monk Turner. Now let me just say that these are not copyrighted songs. They're freely available. There's a website where you can get music and sound files that don't have copyright. I've forgotten what it's called, so I can't tell you where I got these, but I think if you search this Monk Turner in Google, you should be able to find that song. Okay, and the other one too, both from the same website. Okay, so so basically these are MP3 files that you should then put in the default folder that Mathematica calls on. It's usually the documents folder unless you've changed that. Okay, so I've got MT, I've called it MT for Monk Turner, and put that in the documents folder. All right, so let's proceed to do this. Okay, so I'll start with this. A equals import mt.mp3. Okay, and I'll just leave the semicolon off. All right, now look, I mean, I've imported that, so it's a sound file. It seems to be 36 seconds long, but let's see that.
Your birthday, happy birthday. birthday. It's a great day. That's what we say. Happy
Birthday to you. Okay, so that's a silly song for the sake of the exercise. Now, the next command here is b equals audio data a. All right, so now I'm converting that that sound file MP3 into some data. All right, so let's shift enter. This takes a little while because there's a lot of information in that MP3 file. Even though that's only 36 seconds long, there's a lot of stuff in there. So if you've got a 5-minute song, that could take a little while to run this. Okay, so I guess what do we do but have a chat? So, oh well, we don't need to. Okay, it's here. So okay, so we have a list. It's a long list, right? But you want to have a look at the shape of it. It is a list containing 2 lists. I can tell you that because I know from experience with this. It's a list containing numbers but there are 2 lists inside the list. Okay, so let's just put the semicolon back on, and we understand that that's a list of data. Okay, now first of all, let's write just as what's written there. Take B1 9. Okay, so what that says is just show me the first 9 elements of the first list within that pair of lists. Okay, so shift enter, and there is the first 9 elements of that list of data there. Okay, so all right, now next one. Okay, the same thing with the second list within that list. So let's have a look. Copy. Okay, shift enter. All right, now there's another list of data. Now I don't really know what this data represents, but Mathematica can interpret that and turn that into sound. Okay, let's ask what the length of the list is. All right, length of B. How do you spell length? TH. Length of B. Okay, 2. So that tells me that this audio data list is a list of two lists. Okay, so it has length 2, but the data arrays within that are longer. For example, if we say what is the length of the first pair, that'll be a lot longer. You see, it'll be 1.5 million or so in length just for that 36-second soundtrack. Okay, so I'll scroll down, see what we're up to next. Okay, so now we're going to call that len for length. All right, put that in memory. And then len2 is the length of the second pair. All right, which is probably the same. Let's have a look. Yep, that's the same number. Anyway, okay, so then we want to know what is the maximum value within the first array. All right, so I'll put max B1. Oh yeah, I wanted to show you the value of that. What's the maximum value within it? Okay, so 0.82 something. All right. Now, what does that tell me? It tells me how I can filter this. Okay, because I now have access to this audio data. And so that means that I can filter this in the time domain. So this allows you to get rid of some volumes that you're not interested in. All right, so let's just write exactly like that comment, filtering in time domain. Okay, and so let's begin to do that. So I'll set a tolerance of, this is the volume tolerance, 0.0001, and we can change that as desired later. Okay, and then we'll scroll down. Okay, so first equals table, and we're tabulating over j going from 1 to the length, so which we put in memory as len. Okay, and so we'll have a semicolon after that because it'll be a big data list, as we've seen. All right, now we're putting if. All right, this is the if statement. If now what do we want to do if our condition is met? We want to put the element of that of the list, the first list, okay, which is b1, and then the jth element of that, right? Otherwise, if that is higher than our tolerance, or sorry, if the condition is not met, which means it's lower than the tolerance, then we want to replace that number by 0. Okay, so now let's put in the condition. So the condition is that b1 comma j is greater than the volume tolerance. All right, sure. And then let's see, the second list looks just about the same, except that we replace the one with the 2. Okay, so I can copy this and I'll put second for that, just as written, and we change the 1 to the 2. So we're now talking about the second list within that pair of lists. Okay, let's see what we should write next. Well, look, it would be nice to play this back again, right? So let's see if at this point we can do that. Okay, before we proceed to do the rest, so I'll construct a list containing first, second. Okay, now what were the commands for playing? Let's see, I think we need to go here, right? So I'll copy this. And I don't know if this will work. I might need to look in the help file to sort that out, but we'll try it. So I just change that S to what we've got. Shift enter. Running. And I can hear the fan going on my computer, so it's doing quite a few calculations. And then this little thing circling around. Okay, it's completed that. All right, and let's have a look. We have a sound file to play, so let's try it out. So remember, what we've done is we have, before we play it, we have replaced any number in our list that is less than 0.0001. We've replaced that with 0. Right, so probably we're not going to notice any difference in what we're hearing out of that, but let's try. Did I press play? It might be slow to respond. Let's see if the computer's awake. 5 plus 4 is 9. Okay, good. I don't know. So look, let's just change this tolerance. Let's go 0.1, right? That might even be noticeable. So, oh look, it's playing now. I can hear it. Can you? You might not be able to hear that, but what it sounds like to me is it sounds a little bit like the sounds of the movie The Predator. You know, The Predator is a movie about some alien that hunts people. So it sounds a little bit like the sounds in that from memory. Okay, so you can get some unexpected results when you do this. So let's now try this with this new number 0.1 as our tolerance. Shift enter. It'll take a little while. Again. Okay. Oh. Hope you're having a great day. Okay, here we are. Let's play it. Hopefully it works. Not hearing anything, but of course this could take a little while. So while we wait, why don't we... Yeah, I can hear something. Okay, so it's not really quite the effect we might hope for, but you can see what it does. You're throwing away basically some elements of the data set by filtering in this way. Okay, so that can be an interesting thing to do. Now, hopefully that won't go on and on forever. We can do the next exercise. So let's have a look. Okay, now the next thing to do here is I'll press stop and see if that does anything. Okay, seems like it's stopped. All right, so the next thing is something that we haven't really discussed yet much together, which is signal processing. Signal processing is it's a means of translating data like this into a list of complex numbers that represent frequencies. Okay, now sound and music, it's full of frequencies. The data is about frequencies, right? Or yeah, so but when you're doing signal processing, you are turning time domain data into frequency domain data, meaning that the axis on the horizontal, or the horizontal axis, is going to be about the frequency rather than about time or something else, right? So you make a transformation and you turn it into being about or dependent on frequency. Okay, so that's useful because you can do this filtering in the frequency domain, meaning that certain pitches of sound you can throw out by replacing those with 0. All right, or for example, sounds that the human ear can't hear, so there's no point in keeping that in your data set. And in fact, I believe that that's what the MP3 file format does. It throws away certain sounds that the human ear can't hear because there's no point in keeping that data, right? If we can't hear it. Okay, so let's have a look at this. So first of all, I am increasing the volume by 20%. Now I think that's probably safe, but if you're concerned, just take care and turn down your volume if you're going to do this. So let's see, b equals 1.2, and then we're multiplying by first comma second. Okay, and let's have a look. All right, next, this is a built-in function to perform the discrete Fourier transform. All right, which you may or may not know about, but let's just do it. P equals Fourier okay, so Fourier, and I'm applying it to the first list. All right, and then we have an option, Fourier parameters 1 minus 1. So this is just these are just a particular option of how you take the discrete Fourier transform. Okay, so for signal processing, I think these are the parameters that are commonplace. All right, so okay, so we have P equals that. Now Q, all right, basically the same thing on the second list. All right, semicolons. Now let's scroll down. All right, so next we're going to do the filtering part of this. But first, so that we can see the data, let's just take and have a look. Take P, 10. Okay, shift enter. All right, so what we have here are, you see a list of complex numbers. So these this is the square root of -1. All right, which is not a real number. But that's what you do when you take a discrete Fourier transform. You end up with a list of complex numbers, okay, which represent frequencies. Okay, so now this one is close to 0, all right, but the others are not. They do have imaginary parts. Okay, so now that we know what that data looks like, let's say what we're doing, inverse discrete Fourier transform. Okay, so all right, so I'll write this. Now I've got P equals. That's a little unfortunate, but okay, I mean that's fine to write over the top of your variables sometimes. I'd rather not do it, but sometimes you run out of letters, so okay. All right, so let's write P equals. Now RE, it says take the real part of this. All right, so we've let's see, have we done the filtering yet? No, we haven't done the filtering yet. Yeah, so we haven't done the filtering in here, so but it works much the same as what we did before with the volume. Okay, so you basically filter this list of complex numbers. So I'll just write a few notes on how this works. Okay, so filter the complex numbers using ABS function. The ABS function is the absolute value function, right? But it also works for complex numbers, and what it means is the modulus of the complex number, as in how far away that complex number is from the complex number 0 in the complex plane. Okay, so it generalizes the absolute value. So that is perfectly sensible to use ABS for that. Okay, so what you want to do is filter against the size of the absolute value of these complex numbers. So you can say throw away certain numbers by replacing them with this 0, certain numbers that represent frequencies that are too big or too small, or just unpopular frequencies, say. Okay, so I'll just leave that comment as is, and I'll talk about the inverse discrete Fourier transform that's built in. Okay, because that's what we have here. So that brings us to this spot. All right, so you just write inverse Fourier. And then we put P and then put in the same options. P, and yes, we'll include the same options. Okay, so when you take the Fourier transform, you end up with complex numbers, but when you apply the inverse transform, you are supposed to get real numbers, but there are truncation errors in the computation, and so you end up having these little tiny imaginary parts. For example, we scroll down here and look at this. This is an imaginary number right here that is extremely small, as in the coefficient of I is almost 0, right? So that's why I apply RE to this, so that those imaginary parts go away, because I know they're supposed to be real in the first place. Okay, and then we do the same thing to Q and call that Q. So I'll just copy this, paste, Q equals inverse Fourier Q. All right, then what do we have? So after doing that, we can have a sneak peek at, say, the first 10 by using the take function. The take P10. Take P10. Shift enter. All right. So this was the first 10 data points of that other P, and then after this runs, it could take a little while. Okay, so should have had a semicolon there. Anyway, so the first 10 elements of when we applied the inverse Fourier transform to this are a bunch of numbers that are close to 0 by the looks of it. Okay, so hopefully the original P did have numbers close to 0, because if you apply the Fourier transform and then you apply the inverse Fourier transform to that, you get back the original data. Okay. All right, so let's consider this. Okay, we just have a little bit more to write. F equals P comma Q, and then we do the usual sampled sound list. Okay, R equals sampled sound list. F 36,000. Okay, so that's the frequency that we want to play it. Is that the frequency? Come to think of it, I don't know what that is, but I think it's about right for this. Oh, look, I reckon that it's the playback speed, if I remember right. So if you change this, it makes it faster or slower, I think, but investigate that yourself. Okay, and then sound R, and let's go and put the semicolon there, so we don't have to see that again. And let's try it. Alright, so what we've done is we have taken the Fourier transform of the data, discrete Fourier transform of the data. We did not filter the data in the frequency domain, but you can do that. It's just like filtering the data in the volume domain, but you're applying a test on the absolute value, which is the modulus of the complex numbers. Okay, so now we have this, and it should sound roughly the same as the original. Not really. Okay, so to me that sounds a bit scratchy, raspy, however you want to say that. So possibly something I did here with the precision was not good enough to get good quality of sound. So this would take a little bit of trial and error to work out what's going on. Okay, but that's about all for now. I hope you learned something from this exercise, and I'll see you in the next one. Thanks for watching.